Hello everyone. Today we are going to discuss about the Webster's method of traffic signal designs. So before starting to the Webster's design, we should be able to know about some terms and definitions related to it. First one is cycle. A cycle is one complete rotation through all of the indications provided, and a cycle length, it is the time in second that it takes a signal to complete one full cycle of indications. It indicates the time interval between the starting of green for one approach till the next time the green starts. It is denoted by the letter C. Interval. Thus, it indicates the change from one stage to another. There are two types of intervals: change intervals and clearance interval. Change interval is also called the yellow time, amber time, indicates the interval between the green and red signal indications for an approach. Clearance interval is also called all red, is included after each yellow interval, indicating a period during which all signal phase shows red and is used for clearing of the vehicles in the intersections. Or we can say that it is also used for the pedestrians to cross. Green interval. It is the green indication for a particular movement or a set of movements. This is the actual duration the green light of a traffic signal is turned on. It will be denoted by a letter G, something like G. Red interval. It is the red indication for a particular movement or a set of movements. This is the actual duration the red light of a traffic signal is turned on, and it is represented by the letter R. Phase. A phase is the green interval plus the change and clearance interval that follow it. Thus, during the green interval, non-conflicting movements are assigned into each phase. It allows a set of movement to flow and safely halt the flow before the phase of another set of movements starts. So there will be 2-phase, 4-phase intersections, and will be later discussed. So lost time. It indicates the time during which the intersections is not effectively utilized for any movements. For an example, when the signal for an approach turns from red to green, the driver of the vehicle which is in the front of the queue will take some time to perceive the signal, usually called a reaction time, and some time will be lost before he moves. The next thing is a saturation flow. It is the highest amount of flow possible, and it will be represented in the term of PCU. So, introduction. It has been found from studies that the average delay and the overall delay to the vehicle at signalized intersection vary with signal cycle length. The average delay per vehicle is high when the cycle length is very less, as a sizable proportion of vehicles may not get cleared during the first cycle itself. So as the signal cycle time is increased, it seems that the average delay per vehicle decreases up to a certain minimum value, but thereafter the delay starts increasing, indicating that there is an optimum signal cycle time corresponding to least overall delay. The optimum cycle times will be depending on the geometrical details of the intersection and the volume of the traffic approaching the intersection from all the approaching roads during the design hours. So, Webster's method. Webster's method of traffic signal design is an analytical approach to determine the optical signal time corresponding to minimum total delay to all vehicle at the approach roads of the intersection. The field work consists of determining the following two set of values on each approach road near the intersection. The normal flow Q on each approach during the design hour and the saturation flow S per unit time. So the normal flow values will be taken as example Q1 and Q2 on road 1 and 2 are determined from the field studies connected. during the design hours or the traffic during the peak 15 minutes period. The saturation flow of a vehicle will be determined from careful field studies by noting the number of vehicles in the streams of compact flow during the green phase and the corresponding time interval precisely. In the absence of the data, we can take an approximate value of a saturation flow is estimated assuming 160 PCU per 0.3 meter width of the approach road. Based on the selected value of normal flow, the ratio and are determined on the approach road 1 and 2. It is in the case of a two-phase road, and in the case of mixed traffic, it is necessary to convert the different vehicle class in the terms of a suitable PCU value at signalized intersection. In case there are not available, they must be determined separately. So the normal flow of traffic on the approach road may also be determined by conducting the field studies during off-peak hours to be designed different set of signal timings during other periods of the day also as required, so as to provide different signal settings. The optimum signals cycle is given by a relation that is C0 is equal to 1.5 L plus 5 divided by 1 minus Y, where L is equal to the total lost time per cycle, that is in seconds, that is equal to, that is L is equal to 2n plus R, where N is the number of phase, and R is equal to all red time or a red amper time. All red time may be provided for pedestrian crossings, and Y is equal to Y1 plus Y2. Here where Y1 is the ratio of Q1 by S1 and Y2 is the ratio of Q2 by S2 in the case of a two-phase road signal. Then G1 is equal to Y1 small y1 divided by capital Y into CO minus L, and G2 is equal to Y2 small y2 divided by capital Y into CO minus capital L, where G is the green time, and if this is for a two phase, and if similar procedure is followed when there are more number of single phases. So this diagram is showing a typical phase diagram and the details of a traffic signal settings, and we can see that there are two phases, first phase and second phase is an example in which G1 is representing the green time and A1 is representing the amber time and R is representing the red time, and RA is showing the red amper, and you can see that in both the phase and phase 2 the cycle times will be same, and a diagram showing an intersection is shown on the right side, where TS1 is the traffic signal on road 1 and TS2 is the traffic signal on road 2 and PS is the pedestrian signals. So now we can do an example of a Webster's signal design, and the question is the average normal flow of a traffic on a crossroad A and B during the design period are 400 and 250 PCU per hour. The saturation flow value on these roads are estimated as 1250 and 1000 PCU per hour respectively. The all red time required for pedestrian crossing is given as 12 seconds. We need to design two-phase traffic signal as I mentioned above with pedestrian crossing by Webster's method. So in this we have given a flow value at road A and B as QA is equal to 400 and it is already given in PCU per hour, and QB is equal to 250 PCU per hour. So the saturation flow SA is equal to road A is equal to 1250 and SB is equal to 1000, which both are in PCU per hour, and all red time, that is the R value, is given as 12 seconds and the number of phases is 2. So we have to find the ratio, that is small ya, that is flow divided by saturation flow at the road A, that is QA divided by SA, which is equal to 400 divided by 1250. We get a value of 0.32, and for YB similarly Q it is QB by SA, not QA by SA, is equal to 250 divided by 1000. We will get a value of 0.25. So when we are calculating the capital Y is equal to YA plus YB, we get a value of 0.57, and the total loss time is found out by L is equal to 2n plus R, which is equal to 2 into n is the number of phase, that is equal to into 2 plus 12 is equal to 16 seconds. So the optimum cycle time can be found out by the formula 1.5 L plus 5 divided by 1 minus capital Y, in which the L is equal to 16, and by substituting the values of L and Y we get a value of 67.5. so we round it off by 67.5, we get a value of 67.4, and we will be getting rounded it as 67.5 seconds. So initially what we will do is that we will separately find out the green time at road A, that is equal to small y divided by capital Y CO minus L, that is equal to 29 seconds, and for the green time at road B is, say, using the formula, we will get 22.5. so by providing all red time R for a pedestrian crossing as 12 seconds, we will be getting, and providing an amper time of 2 seconds for each for clearance, the total cycle times will be that is equal to 29 of green time at road A and 22.5 at the green time at road B, and the 12 is equal to all red time, that is equal to 12 seconds, and for each amber times 2 plus 2 we finally get 67.5 seconds. So now let's see the phase diagram of it. This is a phase diagram of the signal designs, and from road A you can see that the green time is equal to 29 seconds and amber time is equal to 2 seconds, and the red time is equal to 24.5 seconds at road A, and the all red is equal to 12 seconds. And in road B the red time is equal to 31 seconds, which is the sum of the green time at A 29 seconds plus amber time 2 seconds at road A, and in road B the green time is equal to 22.5 seconds and the amber time is equal to 2 seconds, which is equal to the red time at the road A, that is 24.5 seconds, and an all red 12 seconds is provided. And from the figure itself we can see that there is a movement of the vehicles A, and at that time at road B the pedestrians are trying to cross through the zebra crossing line, and all red time period is used in which all the vehicles will be stopped. At that time the pedestrians will be trying to cross the intersection through the zebra crossing line. So it's a diagram that is showing the all red time period and the pedestrians are crossing. I hope you all understand about the signal design by Webster method. Thank you.